Title: Autonomous Bootstrapping of Quantum Dot Devices. The paper discusses the development of a bootstrapping algorithm for initializing a depletion mode quantum dot (QD) device in preparation for subsequent phases of tuning. This algorithm is essential for enabling scalability as QD arrays grow in size and complexity. The bootstrapping process starts after cooling the device down to a few mK and involves determining the operational ranges, determining charging energies for each quantum dot, QD, and making the local charge sensing system operational. The proposed algorithm uses heuristic approaches to QD device initialization and combines efficient ray-based measurement with rapid radio frequency reflectometry measurements. It is designed to be initiated on a pristine QD device post-cooldown, for instance in the two-dimensional electron gas 2DEG limit. The algorithm closely follows the typical manual tuning steps of a QD device and utilizes a proximal charge sensor measured in radio frequency (RF) reflectometry to improve tuning efficiency and reliability. The bootstrapping process consists of several stages, including preparation, diagnostics and characterization, defining QD channels, setting up charge sensor, and configuration of the outer barrier gates. Once the bootstrapping process is completed, the tuning algorithm initiates the coarse tuning stage, which aims to find a range of gate voltages where the device is in a particular global configuration, i.e., a single dot, SD, or double dot, DD, state. The authors demonstrate that the proposed bootstrapping approach can be highly successful, with 86.5% of test runs successfully preparing the device for coarse tuning. Given the rapid acquisition of data and its efficient analysis, the algorithm is capable of tuning the double QD device within about 8 minutes. Moreover, using the parameters gathered during bootstrapping, they show a 96.6% success rate for coarse tuning, preparing the QD device for further calibration toward qubit operation. Finally, the authors demonstrate the cross-platform applicability of the ML model used in the coarse tuning module, which has only been deployed on CXGE1-XQD devices with an overlapping gate architecture. This work is, therefore, an important demonstration that an ML algorithm trained exclusively using synthetic data can be successfully used to assess the state across various device designs. The proposed bootstrapping technique is initiated with a configuration file that defines the device architecture, identifies the quadrant to be used, and specifies the gate's functionality. A scanning electron micrograph of a gate defined, depletion mode gallium-3 arsenide, Al 0.36 Ga 0.64 as device is used to demonstrate the bootstrapping protocol. The device consists of 4 identical quadrants, each with tunable metallic electrodes for forming 2 quantum dots, QDs, for hosting qubits and a larger sensor QD. The experiment is conducted in a dilution fridge at roughly 30 mK, using a quantum machine's QD-ACII to set the bias on the source ohmic and perform voltage sweeps of the gates. The current measurements are acquired and converted into voltage readings using an Ithacode 1211 current preamplifier and a Keysight 34465 A6.5 digital multimeter. The bootstrapping process begins by localizing the operational quadrant by setting the backbone gate to the most negative safe voltage. The algorithm then assesses the functionality of the quadrant's finger gates by applying a voltage to each gate and measuring the current through the device. The analysis of the current versus voltage signal serves as a diagnostic tool to verify whether gates are functional and suitable for tuning. The algorithm proceeds to define the QD's channels by adjusting the backbone and outer barrier gates to split the QD device quadrant into the sensor QD and qubit QD channels. This is achieved using an RB measurement approach, which involves measuring a collection of unidimensional voltage sweeps initiated from a common starting point. The algorithm picks the angle for which the pinch-off voltage is the lowest and decomposes the optimal pinch-off voltage into the backbone and outer barrier gate voltage components. Once the current channels are established, the protocol proceeds with tuning the outer barrier gates for both the sensor and qubit QDs. The goal of this stage is to detect the Coulomb blockade induced by the formation of the sensor QD, manifested through oscillations in the current sweep measured on the sensor plunger gate. The detected peaks are analyzed to find one that is most likely to lead to a high sensitivity of the sensor, using a score function inspired by Ref. 28. The protocol's performance is evaluated through consistency plots showing mean values and standard deviations for the characteristics of interest averaged over 89 test bootstrapping runs. The pinch-off and saturation values are collected for the gates, and the parking value statistics are collected for the sensor plunger, backbone, outer barrier, sensor top, and sensor bottom gates. The final configuration for the plunger gates is established during the coarse tuning stage. Here is a combined summary of pages 5 and 6. The bootstrapping module is completed by confining a qubit quantum dot, QD, and splitting it with the B gate to form a double dot, DD. The RF reflectometry setup is then turned on for charge sensing, with the plunger parked at the largest slope of the signal reflected off the sensor QD. The coarse tuning stage begins by using finger gate characteristics from bootstrapping to define the operational regime and limit the range of gate voltages. The DSE-based tuning module is initiated at randomly selected voltages for P_L, B, and P_R gates, with the scan size determined based on charging energies extracted during diagnostics. The navigation algorithm within the DSE-based module is driven by the distance between the target state vector P_target and the predicted state vector P, V_R. The state vector quantifying the current state of the device is defined as P, V_R, equals, P_ND, P_SDR, P_SDC, P_SDL, P_DD, where ND indicates no QDs formed, SD_R, SD_C, and SD_L denote the right, central, and left single QD, respectively, and DD denotes the double QD state. The distance between the two state vectors is defined as delta, P target, P, V_R, equals, P target P, V_R, _2 plus epsilon, V_R, where epsilon, V_R, is a penalty function for tuning to larger plunger voltages. The algorithm can take one of three actions based on the outcome of the DSE module. Terminate the tuning process if the distance between P_target and P, V_R, falls below a predefined threshold delta_TR. Adjust the gate voltages for the plunger gates if the distance surpasses the threshold, or recalibrate the sensor QD dot and reinitialize the DSE module if the iteration limit is reached. The auto-tuning is considered successful if the optimizer converges to a voltage range that gives the expected DD configuration when evaluated by human experts. The evaluation of the tuning algorithm is carried out in two phases: testing the performance of individual steps of the bootstrapping algorithm and performing a series of trial runs of the full auto-tuning algorithm in the V_PR, V_B, V_place space. The results show high device and algorithm stability, with low standard deviations of extracted features. The navigation algorithm successfully converges to the DD regime, with the evaluated likelihood of the DD regime increasing as the algorithm progresses. The research proposes and experimentally demonstrates a modular autonomous bootstrapping algorithm for bringing a Gauss spin qubit QD device from an untuned state to the DD global state configuration. The algorithm performs gate characterization, device diagnostics, and prepares the charge sensing QD for RF reflectometry. It efficiently deploys a combination of measurement techniques, including regular voltage sweeps and RB measurements for current sweeps. The algorithm's stability is confirmed by the low initialization failure rate and high consistency of saturation and pinch-off voltages. The results serve as a baseline for the development of a fully autonomous QD device initialization, calibration, and control system for large 1D and 2D QD arrays. Future work includes integrating data quality control modules, refining the RF reflectometry optimization, and extending the algorithm to multiple QD arrays. The paper discusses the auto-tuning of noisy quantum dot devices, a crucial step in the development of quantum computing. The authors cite several studies that have demonstrated the use of machine learning algorithms for tuning quantum dot devices in situ. For instance, Ziegler et al. 2022 proposed a method for robust auto-tuning of noisy quantum dot devices using a physics-informed tuning approach. Similarly, Zwolak et al. 2020 demonstrated the auto-tuning of double-dot devices with machine learning. Moreover, the paper highlights the importance of state identification in quantum dot devices, which can be achieved through a ray-based framework as proposed by Zwolak et al. 2021. This framework utilizes machine learning to identify the charge states of quantum dots. Furthermore, the authors emphasize the need for real-time control of spin qubits, which has been achieved by Barita et al. 2024, using a two-axis control method. This control is essential for maintaining the coherence of quantum information during computation. The paper also mentions the role of machine learning in completely automatic tuning of quantum devices, as demonstrated by Moon et al. 2020. This approach not only speeds up the tuning process but also surpasses human expertise in certain aspects. In addition, the paper discusses various techniques for charge sensing in intrinsic silicon quantum dots, such as the method proposed by Pod et al. 2010. Automated tuning of double quantum dots into specific charge states using neural networks has been demonstrated by Dürer et al. 2020. Finally, the paper highlights the importance of extracting capacitive coupling for quantum dot systems, which can be automated as shown by Ziegler et al. 2023. The QFlow-Lite dataset, introduced by Zwolak et al. 2018, provides a machine learning approach to the charge states in quantum dot experiments. Overall, the paper presents a comprehensive overview of the current state-of-the-art in quantum dot device tuning and control, emphasizing the critical role of machine learning in advancing quantum computing technology.